Right, so this is machine learning for option prices. Presented by Nicholas Jacob on the 15th of March 2021. Okay, so first I'll start with a bit of an outline. So I'll give some background, I guess, about general derivatives. I'll talk about time value of money, then I'll talk about options and option strategies. We'll speak about I'll talk about the normal and not normal distribution. Then I'll mention two traditional pricing models. And finally, we'll talk about pricing options using machine learning. That's some background. So now general derivatives. So first of all, a derivative is simply a financial instrument that has a value that's determined by the price of something else. And the something else is called the underlying asset. And now this something else can be anything like a stock index, an interest rate, like a foreign exchange rate, a commodity like oil, natural gas, corn, aluminum, or anything like that. And even other more weird things like the weather on a given day, or like credit default and real estate. And the uses of this would generally be for, first of all, for risk management. So it's like it can be used by companies or individuals to hedge risk. So for example, if a corn farmer is is expected to harvest a year from now, harvest is going a year from now, he needs to sell it, he can buy buy a derivative that allow him to sell his corn at a particular price to basically hedge against the possibility of the prices going down a significant amount. And I guess it's also for speculation. So if you just think that something will happen, so you think the market will move in a particular direction, you could basically use derivatives that would result in you gaining profit if what you think happens does end up happening. And you can also use it to reduce transaction costs. So sometimes basically using derivatives produces like a lower cost way of undertaking a particular financial transaction. And finally there'll be like regulatory arbitrage, where sometimes you could like circumvent some like regulatory restrictions and taxes or even like accounting rules by using derivatives. And finally, well, individuals using derivatives can use it into like three categories. So there'd be the end user perspective, which would just be like individuals or corporations that just basically try to enter into derivatives for one of the, I guess, uses that we mentioned previously. And then there'll be market makers. So basically, like they're like intermediaries. So if an individual wants to purchase a derivative, the market maker would essentially be on the opposite end of it. So like if someone wants to buy a derivative, the market maker would sell it to them. If someone wants to sell a derivative, the market maker would buy from them. And basically what they get for this is so what they would do is like they would buy low and sell high. So and this is called like the spread, like the bid ask spread. So they would retain the difference between that as profit. So that's, I guess, the compensation for making the market essentially. And finally, there'll be the economic observer who just sort of like observe the market from a more analytical perspective, or even just from a regulatory perspective, just try to get a sense of what's going on. And I guess we'll start with the time value of money, which is one of the fundamental concepts of financial math. So the idea is that $100 a day is not the same as $100 a year from now. So the value must be discounted or accumulated with interest. So if we're looking at the present value of $100 a year from now at a 10% effective annual interest rate, the present value would just be 100 divided by that 1.1. And so how this will be used usually in what's called the discounted cash flow models. You would use the price investment. So for example, if a investment requires you to like invest a certain amount today, and it will generate cash flows at like a specified later dates to determine like the price that you should be willing to pay for the investment. You could use the you could find the present value of all the, I guess, future cash flows and minus the, I guess, the value of the current investment. And also like theoretically, the price of a stock should be equal to the present value of all the future dividend payments, I guess, depending on what you're looking at. So which is generally like well, that's was known as a perpetuity. And then also the price of a bond would just be the present value of the coupon payments, which is the interest payments plus the maturity value of the bond. And then the price of an annuity would be the present value of all the annual payments, because it doesn't necessarily have to be on an annual basis. But also, I guess I'll just note that going forward, I'll use continuously compounded interest rates. It'll be noted by e to the RT, where R will be the continuously compounded annual interest rate, and T is the annualized time. So for example, if we talk about 6 months, T would be 0.5. And so now some examples of derivatives. So the example I mentioned with like the corn farmer, that would be an example of a forward. So basically you agree to carry out a transaction of some underlying asset at a pre-specified price called the forward price, at a pre-specified date called the expiration date. Now futures would be similar to forwards, but they're usually more standardized and regulated. So they usually require something called like a margin account, where you put a certain amount into account at the beginning, and usually with a forward, like the money will only pass on at the expiration date. But here, so depending on whether the value of the underlying asset goes up or down, the long side, so the side that um, the side that would benefit from the increase, the appreciation in value of the asset would basically have money transferred to their account from the other party's account and vice versa. And then we have options, which could be right, but not obligation to buy or sell to sell an underlying asset. So we'll start with considering call options. So call would be right to buy an underlying asset at a pre-specified price called the strike price, and at a specified date, which would be some number of months or years from now. I'm usually doing it T. And so we'll focus on options on stock. Well, I'll mainly focus on options on stock in the stock. Unlike forwards, which, as I mentioned before, the money only passes like at the expiration date. For options, it costs something now called a premium, because if you think about it, the person, like the buyer of the call option, they have the option to sort of just only exercise the option or only use it if it's beneficial to them, and if it's not, they wouldn't. So the other side is kind of always disadvantaged. So you need to provide some initial payments to incentivize them to even agree to sell you the option. And now the payoff of the call would be, so suppose the underlying asset is a stock, the payoff would be the max of 0, and the strike price, the price of the stock at the expiration date minus the strike price. Because, so for example, if the price of the stock is higher than the strike price, what you can do is you'll be able to buy the stock for the strike price K, and then you could sell it back at the price S. So you'll benefit from that. And if the price of the stock is lower than K, then you'll just not exercise it at all, because it won't be beneficial to do so. And also, when you consider the profit, the payoff is just will happen like at the expiration date, and the profit is kind of a more holistic view of it. So you're taking into account the amount that you paid initially for it. So it's the call payoff minus the future value of the premium. And also, so as I kind of alluded to before, options can be considered long or short, depending on whether it's bought or sold. So here I have like the diagram for a long call. So as you can see, like under the strike price, the payoff would just be 0, because it wouldn't be beneficial to the buyer to exercise it. And above the strike price, they will actually benefit. So the difference will be S minus the stock price minus the strike price. And then the profit would just be the payoff shifted down by the future value of the premium. And I guess the short call would just sort of be like the payoff for profit is just like the -1 times the payoff for profit of the long call. And now we'll consider, I guess, put options. This is kind of just the opposite. This is the right to sell the underlying asset at a specified price and at a specified date. So the payoff on this one will just be, so if the price of the underlying asset at expiration is lower than the strike price, you'll benefit, because you'll be able to sell it for K, and you could you'll be able to buy the stock for at the price S and sell it for K. So that's why you do that. If it's, I guess, if the price of the asset is above the strike price, then you wouldn't exercise it. And a similar argument can be made for the profit. And these will be the diagrams. So you can see like as the price of the underlying asset decreases, that's when you'll benefit from the put option. And the short would just sort of be like the inverted flipped along the x-axis. Now, option strategy. So options would sort of open the door to a variety of strategies that can be used in various economic situations that will make so that you can basically profit from speculating, no matter from speculating if you desire to do so. And the price of the strategies would depend on the price of the underlying asset of the options that compose them. So if you look at something like the straddle, for example, this is sort of like you speculating that the market will be volatile. So as you can see, you have the center of it would be the strike price. So you sort of betting that the price of the stock would sort of either go up or down. So you're kind of betting on volatility of the market. And a strangler is similar to it, but so essentially by reducing the initial cost of it, you sort of negate some of your potential profits. So that's why you kind of flatten out your potential profit in some of the case. And a butterfly spread, you're kind of betting on low volatility. And I guess so you can have like a written straddle, which is like a straddle flipped upside down, will be you're betting on low volatility, but on the ends you could potentially lose a lot. So butterfly is kind of like just hedging your bets and reducing the possibility of loss if you're wrong. And I guess a similar argument could be made, I guess, for the other types of strategies based on the shape and everything. I guess now we'll just mention the normal distributions. So come up in a while. So we have the probability density function of the normal distribution is, I guess, this here. And so a normal variable, a random variable, it's a PDF like this is said to have a m v squared distribution. And the normal distribution with m equals 0 and d equal to 1 is called the standard normal distribution, which and here I'll denote the cumulative distribution function of the standard normal as n, just n. And and then given a normal random variable with arbitrary m and v, the CDF of that normal variable can be obtained using the standard normal CDF. So you'll just take the variable minus the mean and divide all of that by the standard deviation, and you end up with the 451. And I guess some of the properties of the normal distribution will be that it's symmetric about the mean, it's stable, which implies that the sum of independent normal random variables will be normal, and the limit of the sum of independent identically distributed random variables is also normal, and this will be regardless of the original distribution. And this is also from a version of the central limit theorem. And I guess in finance, it's often assumed that the continuously compounded stock returns follow a normal distribution. So now we'll consider the log normal distribution. So if y is if x is if x follows a normal distribution, I suppose you have y is equal to e to the power x, then y is set to have a log normal distribution with parameters m and v, and the PDF of that is given as follows. It's pretty similar to the PDF of the other one, except you have like the ln of x in the power of e, and then the denominator you have x, I guess x by v instead of just v. As mentioned before, if we assume that the continuously compounded rate of return, which will denote alpha on a stock, is normally distributed, then the stock price at time t, which is equal to the stock price at the initial time by e to the power of alpha t, and then so st on s0 is just equal to e to the alpha t, and this is normally distributed, log normally distributed, since alpha would be normally distributed. And here the variables that the parameters of it will just be m is equal to alpha minus 0.5 sigma squared by t plus v, and v would be equal to sigma by the square root of t. And I guess I'll just mention that this is for a non-dividend paying stock. If you have a dividend paying stock, the formula will be slightly different. I guess the formula I have down here, I guess I'll just kind of go back a bit and then come. So the expected value of the log normally distributed variable just be e to the m plus 0.5 sigma squared. Since now we have the distribution of the stock price, we could do things like find the probability of it being above or below some value. And to do that, we'll just put it in this form, like st on s0. Since that'll be a log normal random variable, we could evaluate that. We could evaluate using the normal CDF in this form. And as I mentioned before, so m in this case, so here I have m is alpha minus 0.5 sigma squared, and here I have m being equal to alpha minus delta minus 0.5 sigma squared. And the difference is for the one above here, I was considering a non-dividend paying stock, and here it's for dividend paying stock. I guess the difference, the difference is just basically having to accommodate for pricing derivatives on dividend paying versus non-dividend paying stocks, because so for example, in the case of like a forward, you could, in order to own the stock at the end of the period, you could either buy the forward, or you could buy the stock initially and then just wait. But if you buy it initially, you'll essentially get dividends that were paid on the stock that you won't get otherwise. So you sort of have to negate that by discounting by the by this dividend rate here. And so this is the formula that we get this. I guess now we'll talk about, I guess, conditional and partial expectation. And this is just some background for the Black-Scholes formula we'll talk about shortly. So partial expectation of a continuous random variable having PDF f of x, given that it is in a certain interval, is the contribution of the expected value from values within that interval. So it's just the integral from a to b of x by fx dx. So, and then for a log normal variable with parameters m and v, the partial expectation of x, given that x is less than some value k, is just the expected value of x by this term here involving the standard normal CDF. And then therefore, so if you consider the stock price now, which is a log normally distributed random variable, this is supposed to be partial expectation. So I have PE here, but yeah. So the partial expectation of ST given ST is less than K would just be, works out to be the stock price at 0 by e to the m plus the 0.5 sigma squared, and then by this standard normal CDF term, and it works out to be this here. And now the conditional expectation would just be, so the expected value of x given y is the partial expectation divided by the probability of y occurring. And so now for the stock price that we're considering, so the expected value of ST, the stock price at t, given that is less than k, would just be this value here. So it's the S0, yeah, the S0 e to the alpha minus delta t by the n of negative d1, where d1 is the term within the braces here by the standard normal CDF. So we end up with that. And also we'll talk about some of the traditional pricing models, which in this case will be the binomial and the Black-Scholes formula. But so for the binomial pricing model, we'll assume that the price can only move up and down by some fixed ratio u or d respectively its period, and that we sort of use a risk neutral framework, which means that so this means that investors are indifferent to risk, essentially. Like they don't care if something is more or less risky, they wouldn't expect. So usually if an investment is risky, investors would expect a risk premium, which is just like a extra expected return for taking on that risk. So in a risk neutral framework, they don't expect that. So we just discount at the risk neutral rate of return. And yeah, so then the option price, if you look at this example here, so suppose the initial price is 50 and it can move either up to 60 or down to 40. So in this case, it is equal to 1.20 is equal to 0.8. Then the option premium is the present value. So discount back, I guess, if the period is 1 year, it is discount 1 year using the risk-free rate. Just to clarify, the risk rate is just the sort of like the interest rate that you use when, I guess, accounting for the time value of money. So, yeah, so you'll find the present value of what is called the risk neutral probability of an upward movement by the output, by the payoff on the option if the stock moves up, and then plus 1 minus p, which is the probability of the down move, by the payoff if the stock price moves downward. And yeah, so basically you find the present value of the expected payoff. And I guess so if you base these on what's called forward prices, one of the derivatives I mentioned before, P works out to be, I guess, this here, e to the r minus delta by h, where h is the period you're considering, minus d on u minus d. And sometimes I guess you'll just be given a value of, I guess you use some arbitrary value of u and d, but if you calculating it based on forward prices, you'll end up with these values here, which is just e to the r minus delta h plus sigma by root h, or the other one is just minus the sigma by root h for d. And so first of all, just to mention that, so you could use it for like a single period, as with this first example here. I guess just to walk through it a bit more. So the initial stock price is 50, and suppose the strike price of the call was to be 55. Since the call pays off if the stock price is above the strike price, in this case, the payoff will be 60, the 60 minus 55, so the payoff is 5, and in this case, the stock price is below the strike price, so it'll just be 0, because the formula was max of 0, the max of 0 and s minus the k. And this would be example, and yeah, then we will find p and then discount to find the premium. And yeah, so this can also be done for multiple periods. So if we have like 3 periods here, we'll start on the ends, work out the payoffs at each of the end, then keep discounting until they get back to the beginning, and that'll be the price of the option. Next one will be the Black-Scholes formula. So you have a couple of assumptions basically about like the continuously compounded returns being normally distributed, as I mentioned before, and independent over time. So the continuously compounded return on the strike asset, which is the strike asset in this case is just K, which is the value that you'll exchange for the stock. And in this case, it's just the was known as risk-free rate because we're looking at a risk-neutral framework, and the volatility of the stock would be known and constant. I guess that's something I forgot to mention. The sigma here is the volatility of the returns on the stock. Because I mean, whether how much moves up or down by would depend on the volatility of the returns. So the dividends are known and constant, so that's why you can have this fixed value here, which is just the sigma. And so no taxes or no transaction costs or taxes, because that would affect, I guess, yeah, that would just add more complexity that they just not dealing with now. And another thing is possible to short sell. It's also just essentially like borrowing a stock and selling it to buy it back at a later time to potentially profit off of the decrease in the price. And you're also able to borrow any amount of money at a risk-free rate. And now examples, so if you consider a European call option, so how this works is, so this is a European, so European being the style of the option, meaning that you can only exercise at the end of the period. So if you, there are other types of options like Bermudan, which is like they're bounded periods, like specific time periods throughout the lifetime of the option that you'll be able to exercise it. And American, meaning you could exercise it anytime you want, but European, meaning that you can only exercise at expiry, so at the pre-specified date. So if you consider that, we know that the it'll pay off if the stock price is higher than the strike price, which would be K. So in this case, you'll need to pay K if the stock price is above K. And so the probability of this, which I guess we would have derived somewhat before, would just be the N of D2. And I guess the difference between the values that we're using here and the values before would be that I noticed an error in this. So when you see alpha here, alpha is supposed to be replaced by R in all the cases because alpha will be the expected return, which we don't have. And since we're working in a risk neutral framework, all that we would need to be changed to R because yeah, we're assuming that investors don't expect to be compensated for taking on additional risk. So yeah. So anyway, that alpha was in the formula that we would have derived previously. If I just go back over here. Oh, sorry, it's skipping about too much. Yeah. Anyway, you see alpha here, replace it with R for the Black-Scholes formula. And yeah, so the probability of this stock price being above K is just ND2, where we would have defined D2 earlier. And so therefore the expected value of this payment is just the, because since you're paying it is negative, so it's just the K by the probability of this payment happening to occur. And furthermore, so if you receive this, the stock, if the price is above K, and the expected value of this sort of the receipt of this stock, given that the stock price is above K, is the expected value of ST, given that ST is greater than K, of course, and then so therefore the expected value of this payment would just be this conditional expected value by the probability of the condition. So it's just the expected value of ST given ST greater than K by ND2, since we're still conditioning on ST being greater than K here. And this works out to this, I guess, based on what we have derived in a couple of slides earlier. And so therefore the price of a stock, the price of a call with strike price K, where we're using alpha as a volatility, R as a risk-free rate, time period T, and delta being the dividend rate, would just be S by this formula, as you can see here, which would have been, so I guess the rationale for I guess why we use it would have been explained with the partial expectation and the conditional expectation. And so yeah, the price of a European put, which would just be the sort of case where you have the option to sell, would be similar, I guess, but just the condition would be different. So instead of ND1 and ND2, you'll be using ND -1 and ND -2, and the signs in front of sort of like the strike asset K and the stock price S was just sort of flip because it's sort of like the opposite of this case, the negative of this case in a sense. And then sort of, yeah, so now look at, I guess, option pricing with deep learning, this paper by Yang and Key. And I guess sort of some of the background that they would have mentioned in the paper is options can be viewed in terms of sort of the contract details, I spelled that wrong. So that would just be the strike price and the time and information about prevailing financial state, which would just be captured by S, the strike price, R, the risk rate, and sigma, the volatility. And using this, so the option pricing models can be made using only historical data without having to rely on any of the assumptions of like the Black-Scholes model or the binomial pricing model. And when using, so when I guess we use machine learning for option pricing, the final outputs are usually placed into like three categories. So they either directly predict the premium and they sort of supplement sort of the implied volatility. So they input the volatility, like they get the volatility sort of externally and just sort of implant into their model that they use it to make predictions, or they use some other engineered features, or they predict the implied volatility and then use that to sort of plug into the Black-Scholes formula and predict based on that, or they will just predict sort of like the ratio between the option premium and the strike price, just sort of see how the strike price would affect the price of the options. And I guess they also mentioned that MLPs or multi-layer perceptions are just considered to be the workhorse neural network in this area. And recurrent neural networks are often used sort of just to predict the implied volatility, but there seems to be little to no work, I guess, involving just predicting the actual premiums directly using RNNs. I guess the data used. So at the time the authors wrote the paper, there were no open source data sets. I'm not sure they are at the moment. I don't think they are, but so the option and security prices that they use, they obtained it from the Wharton Research Data Services, Wharton Research Data Services. And so to obtain the risk-free rate, essentially, which is like the rate that you use assuming no default. So they use like treasury, the treasury yields from the US Treasury, from the US Treasury Resource Center. And so the reason they sort of use this was because I guess if you could think of as risk-free investment as possible, it would be like government bonds, because I mean, you do expect the government to default on it. And then so the sigma for the Black-Scholes model estimating, or for the Black-Scholes model, was estimated using the historical volatility from the previous 20 trading days. And so they opted to include some data that's in common practice used excluded, which would be like the things that would be considered non-representative examples that would represent like illiquid or extraordinary option circumstances. But they justify this by saying that in other cases, the data set was really small, but they had a lot of data, so they decided why not. And yeah, so in the end, they had about like 12 million examples of roughly 50-50 split between calls and puts, and 9811 training, testing, and validation set split. And so, I forgot to rename this, but yeah. So the models used, we have they named them MLP1, MLP2, and the RN was a LSTM. So this one was just an MLP with 4 hidden layers, each with 400 nodes, and the activations for them were just leaky values. And the output in this case was just one node and what's called the equilibrium price. And this used rally activation. So the equilibrium price is like, so as I mentioned before, with like the market makers basically benefiting from the bid-ask spread, the equilibrium price will be considered like the fair price and the kind of price in between the bid and the ask price. So that's what they predicted with this first one. The second one, it was like a multitask learning problem where they had 2 output nodes. So they predicted the bid price and the ask price and the LSTM. So the model so they wanted to estimate, instead of just using the estimates of the previous 20 days of historical data as before, they wanted to sort of get a better estimate of the volatility using a LSTM to see if it will improve it. So they used like an 8-unit LSTM to take the closing prices at each of the time steps, or 20 time steps. Yeah, I believe they did it since in the other cases they used like 20 days, so they just use this, and I believe after they did it, they passed it through like an 8-unit LSTM like 3 more times, and then the final step they used the like these. So yeah, so it's just after the final one, they would like get a volatility from that, and they would input it into the MLP1 as the volatility that I will use in that model. I guess sort of here I have a look at the architecture that they use. So they have like the actual data, and they'll pass it through the initial one and the 3 following ones, and they'll get essentially have volatility value here, which would be part of like the financial state information that we pass into this the 4-layer MLP here. And yeah, this in MLP1 they predicted the equilibrium price, of course, and sort of the results, I guess, are kind of interesting. So they use some, I guess, not, I guess, some non-standard definitions for some of the, I guess, what I thought was just like standard MAPE, but the MAPE in this sense meant like median absolute percentage error, AAPE was average absolute percentage error, bias which is the median percentage error, and PX was the percentage of observations within plus or minus X% of the actual price. So I guess if you look at it, I guess the one that pretty much like stands out the most to me is kind of the PE5. So the Black-Scholes model, we have like about 50% of them being within 5% of the actual price. So for the first MLP, we had like 61%. For the second one, we had 63%, and it sort of decreased for the LSTM. And I guess the performance would, the numbers would increase as you increase the percentage, of course. And I guess even if you look at the MAPE as well, the MLP2 seemed to perform the best. I guess another thing that sort of stood out to me was the difference between the puts and the calls. So if you look at the PE5 for the puts and the calls, like so theoretically, I guess they sort of teach that the price of a put or a call could be derived from the other. So if all other things being equal, so like if you have a put and a call with the same strike price based on the same underlying asset with the same time, you can sort of derive the other. So I didn't expect that the performance on them to be so vastly different. So I guess that was an odd thing that I didn't really expect to see, but yeah. I guess I didn't see a paper on this, but just like a sort of an idea. So in an article, and it's just using GANs prices. So the generator would basically create stock path trajectories, and I guess we'll just have its usual rule of it's trying to determine false from the real ones from the false ones, and the end result would basically be a model that could generate realistic stock path projections, and then have the GAN generate a large number of possible stock path trajectories, and then since the sort of the option can just be priced based on the, I guess, the present value of its payoff. So similarly, the payoff essentially by getting the stock path trajectory. And so find the payoff given the strike price and everything. Discount back, so you get the prices of, I guess, a bunch of simulated options. And then so average over all of these to get like a fair price of this. And yeah, so that's the general idea. I guess I'll like to play around with this, like, I guess, and see what I will actually come up. I haven't done it yet, so I'd like to look into that. And these will be some sources, and thank you for your time. And yeah, so no, I'll take any questions.
Yeah, I guess I'll start off as usual. Yeah, interesting talk, Nicholas. So the GAN stuff at the end there, this is something you plan to have a look at, or you've seen papers on it already?
I haven't seen a paper on it. Just like an article mention it, but I'll definitely try to look into it and see.
Okay. Yeah. Yeah. No more questions, but nice talk. Thanks.
Thanks, bro.
My mom was a derivatives attorney, and I have to give her more credit.
I mean, these are just like the basic derivatives, because like some of the derivatives that I've seen, like they just get wild. Like these are the team ones. Like some of them just, I'm still trying to wrap my head around. Like some of them, I'm like, I don't know how to price them, but these are the most. I haven't seen. I don't think I've seen any papers like on pricing like the more exotic types of derivatives or options, or even like what's called the real options. It's like it seems like they just give it like real life scenarios, and like they try to estimate like the price that they should pay for the alternatives or the trade-offs, and it can get pretty weird, but yeah.